Hey everyone, my name is Marcus, I'm with Datadog, and this presentation is going to be about things that I've learned over the past years using Flight Recorder, and especially the things that I've learned over the past 2 years working with Flight Recorder at an immense scale at Datadog. So the agenda is pretty simple. I'll start with a quick introduction to the Flight Recorder, and then I'm going to move over to lessons that I've learned and hopefully end with some demos. We'll see if there is time. So the Flight Recorder can be thought of as the data flight recorder of a modern aircraft. The black box that is recording things that is going on in the cockpit, and different sensors like altimeters and stuff like that. But in this case, of course, it's recording what is going on in the Java runtime and what is going on in the application running in the Java runtime. So for the runtime, it might be recording things like compilations and garbage collections. And for the application, it might be recording where the application is spending the most time on CPU, or where you have thread holds. And it does this at a very low overhead, of course, because you wouldn't want your application to totally change behavior just because you have the Flight Recorder running, just like you probably wouldn't want your plane to do that. So it does all of these things at a very low overhead. And there is a whole lot of APIs for controlling the Flight Recorder or contributing your own data into the Flight Recorder. And there is also a whole lot of different tooling available. So you have the JMC, there is also tooling included with JDK. And the Flight Recorder can be used to solve quite a range of different problems. And I'm going to be mentioning a few of them later. So this all started a long time ago with a Swedish little runtime called JRocket. It was, not going to spend too much time on this slide, but it was initially used to figure out what was going on in the runtime, what kind of applications and how the applications were utilizing the runtime. So we used it as a tool to optimize the runtime itself, not to find problems in customer applications. Of course, since there was a bit of an interest in this from customers and we needed money, we were a small Swedish company, we productized it and we called it JRocket Mission Control. And after a few acquisitions, Oracle owned JRocket, and after that, Sun was acquired by Oracle, and then the JVM teams merged, and then it was rebranded into Java Flight Recorder and Java Mission Control. And when this all was open sourced, it was rebranded because there were some concerns regarding registered trademarks and registered names or something like that. And it was rebranded into JDK Flight Recorder. And it was eventually backported into OpenJDK 8. So if you have OpenJDK 8 or above, you can be using the JDK Flight Recorder. And if you have Oracle JDK 7 or above, you can use the Java Flight Recorder. Anyways, so inside there is a recording engine which record events into thread local buffers, and when those are full, they are copied into global buffers. And when those global buffers are full, you can either configure it to emit these buffers onto disk into a file repo, or you can just keep on overwriting, reusing those buffers. So I mentioned that the overhead is very low with Flight Recorder, and there is a bunch of different tricks that is being used to keep it down. One is to use invariant TSC for timestamping, so the timestamp counter is in the CPU. It's also using thread local native buffers, as mentioned in the previous slide, to record the events into. It's using a very efficient format. It's not doing a lot of work when serializing these events into the buffers. It's using LB128 encoding to keep integer sizes down and some other tricks, but it's a very fast, quick, hands-off kind of serialization format. And it doesn't do much when it's emitting these buffers to disk either, by the way. It's also collecting data very cheaply, so much of the data points that are captured are already sort of it's done in the path where that data occurs. It's not like we need to go, through the entire heap again to find some pieces of information. We can piggyback on things that are already happening in the runtime, which makes much of the data very cheap to produce. And also, since it's built into the JDK, sometimes some abstractions can be skipped and internal data structures used. Really, the API is the event and the event layout. So sometimes it can be cheaper just because of that. It's also trying very hard not to change the runtime characteristics. So for example, if you built a very naive allocation profiler, you would likely undo any chances of scalarization optimizations, whereas that won't happen. Your GC behavior won't just change radically because you moved over and turned on the flight recorder. So some other interesting properties of JFR is that they are self-describing. The chunks, the individual chunks of information that are produced by the flight recorder are all containing the metadata required to be able to parse them. So the layout of the events, type information, metadata, it's all in the individual chunks, and they're repeated. So you don't need to go to the beginning of time to find definition of a new event. When it was defined, that information will be readily available in every chunk. And these chunks are also self-contained, so all the information that you need to be able to resolve a chunk is in the chunk as well. So for example, the constant pools. And there are some different ways that you can do chunk rotations. One of them is starting or stopping a recording. You can get a new chunk by creating a snapshot. You can do it by changing where the file repo is located. And there's a bunch of different ways to do this. This will be required information for later in the talk. And a flight recording itself is just a number of chunks, one or more. So every chunk itself is in itself a flight recording. Cool. So I thought I'd do a quick demo of the flight recorder. Okay, so in this demo we have a recording that I've already opened, mission control, and as you guys can see, there's a lot of monitor enter events here. So Java monitor blocked. We're waiting to enter monitor here, all over these different places. And one thing to note here is that it's not just stack traces here. Of course, obviously we can see the stack traces here. They're not terribly exciting because it's a demo, but we can see how we ended up waiting to enter this monitor. But even more interesting is that we actually have some information about the exact time we waited on this monitor. We can see the monitor class, we can see the previous monitor owner, the monitor address, all things that might help us resolve this problem. So in this case, we can see, we're obviously having a lot of synchronization on this logger, and it's just one instance that we're blocking on for all of these different threads, and we can see the stack trace to it. I'd also take the opportunity, I have another recording here, and the only reason for that is that I wanted to show you that, hey, we also have pretty graphs in mission control, and flame graphs also. So whatever we click, we can now get flame graphs for them, and we can also get graph views, a nice zoomable graph view. Okay, so that's enough for demo. Okay, so lessons learned. One thing to note is that all of these observations are from running JFR at a scale that is ridiculous, with all kinds of loads, all kinds of applications, from the thousands and thousands of threads to effectively single-threaded to high allocation rate ones to basically pretty much mostly waiting. There are all kinds of applications represented here. So for you, with your kind of services, these might be edge cases that you would never run into. So that's worth noting. Also, at Datadog, we really want to be able to support the use case with continuous capturing of all of this data. So there is a couple of different reasons for this. One is, of course, it's really nice to always have actionable data when something goes bad and having it readily available. And also it's great to be able to break down data. If you have all the data available, you can provide context for the data and you can break it down in whatever buckets you want to, which is of course very nice, especially for distributed tracing. And you also capture a continuous stream for data and analysis and statistics. So you don't need to remember to engage data capturing just because you did a new version of the product of the service, or it happened to be Black Friday and you wished you had the sense to enable the profiler. So there are multiple good reasons for wanting to capture all the profiling information. And the question then is that even economically feasible? What would the data rate be? What would the actual performance overhead be? So the cool thing is it actually works surprisingly well at a pretty incredible scale. We're intaking terabytes of JFR data every minute at Datadog, and we're intaking the data from every Java process that is running the profiler. And the recorded data size is about 5 megs per minute, 2 megs compressed. That corresponds to approximately around 100,000 events. And normally we collect 1 chunk per minute. And the CPU overhead is usually less than 2%. And the cost for continuously repeating the metadata is about 0.5%. So the price we're paying for being able to provide the data to be able to parse whatever data is recorded in the Flight Recorder at any given time is pretty low. It also allows us to, we don't need any state. We'll always have the data available to parse any kind of recording, which is pretty nice. So regarding the compressing of recordings, a colleague of mine, Jaroslav Bashrik, figured out for us which the best compression algorithm would be. And we weren't just interested in being able to compress them a lot. Quite contrary, we really wanted to go for something which spent the least amount of CPU cycles over at the client, but still providing a decent compression ratio. And for us, that turns out to be LZ4 with the default settings. So the recording size here is just small is a 1.5 megabyte recording, large is 5 megabyte recording. And the throughput is not normalized, it's in recordings per second. And the compression ratio is, of course, how much smaller recording became. And for us, it really is LZ4, but that does the least damage over at the client. It's fairly efficient. Okay, so exception profiling. Starting with exception profiling. So the built-in JFR exception profiler can be configured to capture all exceptions or just errors. And we thought, errors, how many can there be? So why don't we just enable the exception profiler for errors? Well, according to the Java language specification, error is the superclass of all the exceptions from which ordinary programs are not ordinarily expected to recover. So you would be excused for thinking that there shouldn't be that many errors thrown in an application. Well, that's not quite true. So one of the most popular and widely used Java libraries, used quite a lot internally at Datadog as well, threw an enormous amount of errors. There was a subclass named lookahead success. It was used for control flow in a parser. Outside the ivory tower, not every program might be, in compliance with the Java language specification. But the exception profiling was actually great. It was great to be able to capture both, uncaught exceptions and caught exceptions and see how much was actually being thrown and optimize so that there were less of them thrown, because many of them were thrown where they wouldn't need to. So we went ahead and invented our own new exception profiler. So the new exception profiler has two different kinds of events. One is getting exceptions per type. So we emit them at chunk rotation. So on new chunk, well, we get a event for each of the exception types and get a count for them. And we sample the first thrown exception of each type. And then we try to subsample to hit a certain target rate. So we're using inspiration from PID controllers to try to get these events evenly spread across time. We'll talk about this a little bit later when we do the allocation profiler, because we later built a new allocation profiler for JFR, and we were inspired by the work that was done for the exception profiler. Okay, so a little bit later is now. Allocation profiling was introduced in JFR quite some time ago, in 7U40, when it was still JDK Flight Recorder. And to not have too severe performance implications and to not emit too many events, it uses two paths through the allocation profiler that isn't hit all the time. One of them is when a new thread local area buffer is retired, and the other one is when we need to directly allocate something outside of the TLab, for example, when we directly allocate some big object on heap. And normally this has a really good performance, runtime performance and data production rate. But these days though, you have these 96 plus core beasts that are allocating like crazy on every core, and you know, you might run into edge cases where you simply get too much data. Actually, first of all, we had a performance problem. So there was a hash code bug regarding the JFR constant pools that we ran into, which caused us to use way more CPU than necessary when walking the stacks. So once that was fixed, the CPU overhead of using this wasn't too bad, but we still produced way more data than we could handle. So we needed to have a means of better controlling the data production rate. And the solution to that was, to use the PID controller inspiration here as well. So we added a new allocation profiler to JFR and JDK 16 and above. So first, we got inspired by the JVMTI riff-off of JFR. So in JDK 11, JVMTI got an allocation sampler that uses the same code paths as the JFR TLab events, but it doesn't take each and every one of them. You can specify the average amount of memory allocated between the samples that you get. So that's a really nice thing to do, but eventually you probably want to get them to be emitted at a constant rate. So again, we used inspiration from PID controllers to try to control the data production rate. That gives us some really nice qualities. We have a controllable data budget for our samples. They get spread out nicely over time. We get actual individual samples with, what kind of thing we try to allocate, the size of the thing we were trying to allocate, the time and thread it was allocated in. But we also have the amount of data allocated since the last sample, so we can still, use that information for weighting, for getting the total allocation pressure and get a nice view of that. So, as I said before, if you can provide context, and since we're still getting hundreds of events per second, even with this approach, we can break down things, even allocation rates, if we wanted to, per let's say, distributed trace. In this case, we're actually not breaking it down per trace, because if you do get a garbage collection and you're spending a lot of garbage collection time in your actual span in your distributed trace, you probably want to know where that garbage was created, no matter which thread created it. So here we actually don't break it down. So this is a really stupid example. Anyways, I'm getting tired. Let's go over to CPU profiling. So, CPU profiling, we have execution sample events. And they are really nice in the sense that they are extremely cheap, both in memory and overhead. So we have a pretty much constant overhead. We don't sample each thread. We're sampling a few of them every time, a constant amount. And they are not safe point biased, so we don't require a safe point every time we try to sample something like you would need to if you use the Java APIs that are available for getting thread stack dumps. So that's all very good. There are a few cons though. One of them is we're not sampling every single thread. So for example, JVM native threads, native library threads, they will not be sampled. So you won't get a perfect mapping to the CPU time. And even though we might be able to compensate some of that unaccounted CPU time using other events, it's not perfect. And we don't get native stacks. So we think that JFR would do quite well with a proper CPU profiler that takes a sample when a certain CPU time has elapsed, no matter which thread. And there are some really nice APIs today, for example, Perf Open on Linux, that are backed by PMU, so hardware. If you're not running in a container, so not sure how often that would happen, realistically speaking, today. But we think it would be extremely useful to have something like that in JFR. Okay, so as was shown in the demo, JFR has events for thread holes of various kinds, and you get some contextual information as well. You don't just get the stack trace. You get the stack trace, you get wall clock timing for monitor enter, you get the monitor class and the monitor address. So you can see if there's more than one instance there. And for socket reads, you would be able to get the amount read, so number of bytes read, and the IP address you read from. So these are obviously very useful things, useful information to have when you're trying to track down a problem. But of course, these can happen too often, and JFR has one way to limit this output, limit how many events are emitted. And the only way you can do that in JFR today is with the threshold. Now with JDK 16 and our rate limiter, you could actually use that in more events. So hopefully we'll have that in the future. But this thresholding is problematic because you will always run into edge cases. For example, if you have an application that has 10,000 threads and you have parks, and each park is like 11 milliseconds and your threshold is 10, that's probably an amount of events that you're not prepared to pay for. So even if it's not necessarily a CPU overhead problem, it's definitely going to produce more data than you would want. And you also have a statistical skew. What if all your parks are at 9 milliseconds and your threshold is 10? You're not going to see them. So it's very hard to know if you actually missed something. So it would be nice if the flight recorder had a wall clock profiler. It doesn't today. So you could use both of the best worlds. You could subsample and rate limit the events, the PID thinking. Woohoo. You could also add a proper wall clock profiler for JFR, and you might even make it so that customers and whoever would want to could build their own dynamic wall clock profiler easily using JFR. So one way to do that would, for example, be to add a commit method on the event class that committed the event on a separate thread. So it would use the thread, sample the stack trace, maybe even allow it to, with an extra annotation, to get the thread state and record that. That would be a nice addition to the API, and then everybody could sample things however they want to. It could be a separate little Java thread, just picking threads and sampling them. Okay, so the last thing I thought I'd bring up is the old object sample event. So for those of you who don't know, the old object sample event is a very interesting event for solving memory leaks without having to do full heap dumps. It's sampling instance allocations. You get the allocation stack trace, you get the allocation type and time and type, and you can also, when you dump the events, you can calculate the reference chains back to the objects. So you pretty much get everything on a silver platter that you might want to use for or need for solving a memory leak. There are some problems though, because the allocation stack traces will survive for much longer than just a chunk. The constant needs to be stored somewhere where they can be stored for longer. And the current problem is twofold. One is the stack traces are always sampled. So whenever you might consider to sample an object sample, you will capture the stack trace. And the second is constants that aren't used anymore will never be cleared. So these can grow very quickly and grow very large, and they won't shrink. So you can't really use the old object samples events currently for continuous profiling until we've solved that problem. Luckily, there is a solution coming up. So, reference counted site table will probably be committed over the next month or two. So then we can start using the old object sample for continuous profiling as well, which is awesome. Okay, so I wildly overestimated the amount of content that I would be able to cram into this presentation, so there will sadly be no nice demos of all the cool things we're doing at Datadog with this technology. But I'm going to provide some links to things and to a blog post that I did about continuous profiling and diagnostics, so that you can go check it out, or you can just try out the product and see all the good stuff that we do. Anyways, so first thing that I thought I'd mention is that JMC 8 will be released, at least source released, by the time that this presentation is held. It's up to the downstream vendors to provide binary releases, and that might take a little bit of time, but you can at least build the build yourself, or you can, maybe it will be released with binary releases by then too. We'll see. Anyways, there is a tutorial that you can use to learn more about Flight Recorder and Mission Control. It's on GitHub, and feel free to fork and do pull requests for things that you want to improve on that tutorial. And there is also a nice JShell example for using JMC Core, so the parser and the statistical tools, together with flight recordings of flight recorder events, and that is also on GitHub. So here are some interesting links that might be useful. One is the GitHub repo for OpenJDK JMC. If you want to go to the JDK, it's of course OpenJDK JDK. My blog, where I sometimes write about things that are related to JFR or serviceability or mission control. And the last link is to my Foojay.io blog on continuous profiling. So I think I'm probably out of time now.